Hello everyone, welcome to the 7th video of 10 AP Physics 1 summaries. Today we'll be looking at the torque and rotational motion unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I will include timestamps in the comments for each topic. Let's get started. Rotational motion is basically linear motion put around a central axis. There are so many similarities that we will dive into, but it's important to keep in mind that the same concepts still apply, they're now just angular. A good way to think of this is polar versus Cartesian, or coordinates in the form r theta instead of xy in math class. It is just another lens for concepts we already know. The first step in understanding rotational motion is torque. Put simply, torque is rotational force. Just like force creates linear acceleration, torque creates angular acceleration called alpha. Like all rotational and linear analogs, torque and force are related by a factor of radius. Imagine standing in front of a door. How would you push on the door to get the most rotation from the least force? Try it for yourself. You will find the easiest way to rotate the door is by maximizing radius by pushing near the outside edge of the door and pushing completely perpendicular to the door. If you push at an angle, only some of your force will translate to torque, specifically the perpendicular component of your force. Let's look at a diagram of this. If we compare this yellow orb that has some blue force exerted perpendicular to the rigid bar the orb rests on, to this orange orb that has the same blue force exerted at an angle, we'll see only this maroon component creates torque on the orange orb. Lastly, torque is used in this angular version of Newton's second law, alpha equals net torque over the rotational inertia. We'll speak more on rotational inertia shortly. Just as we can assign force vectors directions like positive and negative, we can assign torques positive and negative directions based on whether they are clockwise or counterclockwise. And this follows the basic rules of polar graphing, which means that counterclockwise is positive and clockwise is negative. So let's do a quick math review just to make sure we remember the principles of angular displacement. Remember that 360 degrees equals 2 pi radians, and as you can see here, I broke that up into quadrants. Now to check our understanding, where is theta equals 3 pi over 8? We can see the pi over 2 line up top, so 3 pi over 8 must be 3/4 of this angle shown by this red dotted line. Now where is negative 13 pi over 8? When we look for a negative angle, we travel clockwise from the same line theta equals 0 instead of counterclockwise like we did above. This ends up being the same line as the angle we found earlier, just found from the opposite direction. We can check that this is true by seeing if the sum of their magnitudes equals 2 pi, and it does. So let's get some practice here with torque. Assume two wheels, this inner wheel and this outer wheel, are connected with a total rotational inertia of 1 kilogram meter squared, starts at rest, and we're trying to find its final rotational velocity 5 seconds after release. So what do we want to do here? If we are looking for a change in rotational velocity over time, then we are going to be working with rotational acceleration. And to have rotational acceleration, we need torque. So let's use this diagram and these values to find the net torque. If we start with the larger mass, then we want torque counterclockwise equals the force that this mass is creating, which would be the weight force of the larger mass. So mass times gravitational constant times the radius, which is r, and this is equal to 10 times, I'm going to approximate g to 10 meters per second squared, so we're going to get 100 Newton meters counterclockwise. Now for the second one, if we're looking and working with the smaller mass, we have torque clockwise equals mg times r, again because we're working with a weight force, but in this situation our mass is 6 kilograms, not 10. G, we're still going to approximate to 10, and then this R is 2 meters. And then we get 120 Newton meters clockwise. So if this is counterclockwise and this is clockwise, we are looking for a difference because they're moving in opposite directions. So the net between these two values would be torque net equals 20 Newton meters clockwise. Oops. Now that we have the net torque, we have the rotational inertia, we can find what the angular acceleration is. So alpha equals the net torque over the rotational inertia, which is equal to 20 over 1. equals 20 radians per second squared. So now that we have alpha, the rotational acceleration, we are looking for a change in omega. So just as we have regular acceleration equals delta v over t, we have angular acceleration is equal to delta omega over t. If we have this equation, we can just plug in chug and do 20 equals delta omega over 5. Therefore, we move up here, delta omega equals 100 radians per second. So our omega final equals 100 radians per second because our initial was 0. So this is what we are working with. This is the kind of problems we are going to encounter. Let's keep moving. So as you've probably noticed by now from the equation and from the practice problems, when we're working with rotation, where we would usually see m in our linear problems, we're instead seeing I. So what does this mean? Moment of inertia is also called rotational inertia, and it is the rotational equivalent of mass. This is more obvious when you realize that almost all dynamics calculations we do are based on inertial mass, not just the irrelevant quantization of matter we tend to think of mass as. Now, you do not need to memorize these equations. They will be provided to you on the exam, and I know that I definitely just referenced my reference sheet when it came to these because they can be overwhelming. However, you should notice that all of the equations follow the form of some coefficient times mass times radius squared. The coefficient is based on the distribution of mass about the axis of rotation. Basically, the farther the mass is distributed from the axis of rotation, the higher the coefficient and the larger the rotational inertia. So let's take a closer look at some examples. Remember that alpha equals torque over rotational inertia. I affects how torque translates to angular acceleration. So if the mass is farther from the axis of rotation, more torque is needed to create an angular acceleration, like in the case of the green hoop and the red hollow sphere. This causes them to accelerate slower, and you can see that because when all released at the same time, they finish afterwards. On the other side of things, the solid blue cylinder and solid yellow sphere have their mass generally distributed closer to their central rotational axes, so they accelerate faster. This makes sense because torque is proportional to radius. If the average radius the mass is distributed at is lower, the torque needed to accelerate it will also be lower. These are equations for this unit. Feel free to take a moment to jot them down, but many of them can be easily found from their linear counterparts, so much so that there are only 3 new equations highlighted in yellow. The first is the torque equation that we've already gone through, the second is the generalized form for rotational inertia down in the bottom left, and the third is a way to convert between linear velocity and period. Once you can identify that this third equation is just a different version of velocity equals distance over time, you should be good to go and understand that the equations of this unit are not something to stress over. I would definitely encourage you to take the time to look at the black rotational equations and their red linear analogs to make sure that you can go between, but once you've got that skill down, you should be good to go. If you are wondering why we can so easily convert between the black and red equations, it's because linear and rotational counterparts are connected by the central tie between angle and arc length distance, which is the radius. This is shown in the upper right-hand corner. When you convert from an angle to a distance, you can think of how far you would have to unroll a circle circumference to cover that distance. Angular momentum's name is pretty self-explanatory. We looked quickly at an example of this in video 5 on momentum regarding a spinning top. Intuitively, we know that a spinning top has momentum that makes it keep spinning. The only tricky part of this is the direction. Angular momentum follows the right-hand rule. It means that if you take your right hand and wrap your fingers around the axis of rotation so that your fingers curl in the direction of rotation, your thumb will point in the direction of L, the angular momentum. While identifying the direction of L can be important, you will most likely just work with the conservation of momentum. For example, look at the Olympic skater. By varying her rotational inertia by spreading and collapsing her limbs, she can vary how fast she spins by virtue of the law of conservation of momentum. If momentum is constant, and we know that rotational inertia and omega contribute to it, when one varies, so does the other. So speaking of skaters, we have a classic example of what the AP likes to throw at us to show the law of conservation of momentum. We have a skater who is varying her rotational inertia with the intent of varying her omega because she knows the law of conservation of momentum, probably. So if we have L initial equals L final, which is basically a simplified version of the law of conservation of momentum rotationally, we know that we have I, or her initial rotational inertia, times her initial omega is going to equal the product of I final times omega final. If we just plug and chug, we can see that by shrinking her rotational inertia in half, she actually ends up multiplying her final omega by 2. So 9 equals 1.5 Wf by 2 is 6. You can try this for yourself at home, actually, by sitting in a spinny chair and having a lab partner spin you around really fast. And then if you spread your arms out, you should slow down. And then when you pull your limbs back in, you actually speed up. It's a really fun way to try it for yourself at home. This brings us to our final topic, the last trait of static equilibrium. The first being zero net force, the second being zero velocity, assuming static equilibrium and not kinetic equilibrium, and the third being zero net torque. So let's try some examples. Does the left meet these criteria? The torque from the force on the left is the product of 2F and 1R, making it 2FR. The torque from the force on the right is the product of 1F and 2R, making it also 2FR. Because the opposite torques cancel out, there is zero net torque. We have to make the distinction, rather, that the bar is weightless because otherwise its weight force could create an additional torque depending on the location of its center of mass. So yes, this is an equilibrium, assuming the bar is weightless. Now what about the one on the right? The red vectors representing forces are clearly unequal. While there may be no torque involved, this fails to meet the first criteria of equilibrium, and so we can say no, it is not an equilibrium. So just as one last example, I pulled a common AP question that is often asked where they are looking for the forces that are being exerted to keep a bar in static equilibrium. For this type of question, you need to know the conditions of static equilibrium, and then you need to know the very important point that you can pick any location on a bar as a pivot point to measure all torque moment arms from. So what this means is if you're trying to solve for these forces, you could choose the location of one of his hands or even the location of the center of mass as a pivot point, and by doing so eliminate that torque from your calculations. For example, if you choose his right hand FL as a pivot point, you would only need to calculate the torques from FR and W, and this can often simplify your work. So just be sure that when you're confronted with these types of questions that you make your job as easy as possible. A bit of a longer video today, but well worth it. In my next video, we will be moving on to Content Area 8, Electric Charge and Electric Force. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.